Okay, welcome back everyone. We have two talks before we head off to lunch. The first one will be Hugo Moeneclaey, who's going to tell us about differential geometry in synthetic algebraic geometry.
Yeah, thank you. So I'm here to present some joint work with Felix Cherubini, Matthias Hössler, and David Verne. And so it will be more synthetic algebraic geometry, basically. And so here I'm talking about a project which goal is to import techniques from differential geometry into synthetic algebraic geometry. So you can find a draft on Felix GitHub, but there's actually a lot of stuff in this draft, and so in this talk I will focus on a fairly narrow part of it. And so this part is a smoothness for affine schemes, so I will explain what this means. But maybe the main point is that here I'm not trying to give an overview of the project, but I will rather focus on giving a couple of interesting synthetic proofs to give you more of an idea of the flavor of reasoning in synthetic algebraic geometry. And so maybe what I should do first is give a very vague intuition about smoothness. So I think the easier way to understand smoothness is as the absence of singularities. So for example, this curve here is smooth because there is no point where something unusual is happening. This one here is not smooth because you have this intersection here. And this one here is not smooth as well because the curve goes back at this point. So here you have a singularity. And so, okay, so the way I will proceed is that I will first give a quick introduction to synthetic algebraic geometry. Then I will give the abstract definition of smoothness for any types. So this definition is maybe a bit surprising and counterintuitive. But then I will explain how, in the case of a affine scheme, which are the simpler objects of algebraic geometry, this has some natural and expected consequence. Okay, so first, synthetic algebraic geometry. So basically, it consists of homotopy type theory plus 3 axioms. So the first one is that there is a local ring R. So yeah, so we call this ring the base ring, and everything is parametrized by it. And so first remark is that the ring R is a set and not a higher type, so we are not trying to do any derived algebraic geometry here. Another remark is that the fact that the ring is local has nothing to do with the actual base ring in the semantics. Actually, it has to do with the fact that we consider Zariski sheaves. Okay, so now let me define a affine scheme. So first, for any finitely presented algebra over the base ring R, so algebra and modules are always over the base ring R, and I never write it. So then we define what is called the spectrum of the algebra, which is the set of morphism of algebra from A to the base ring. Okay, so let's give a quick example. So say the algebra is the quotient of Rx by a polynomial in X P. Then using the universal property of this algebra, one can see that the spectrum of A is actually the type of X in the base ring that are roots of the polynomials. And so then you can define an affine scheme as a type that is of the form spectrum of A for some finitely presented algebra A. And so this is actually a generalization of the example I give, where you look not at roots of one polynomials, but at common roots of a family of polynomials in several variables. So you can use whichever, both are equivalent in this case. And actually they are equivalent because of the second axiom, which is called duality. So duality, it says that for any finitely presented algebra, you have a canonical map from A to map from spec A to R. And it says that this map is an equivalence. And so maybe this duality is best understood through a couple of easy consequences. So the first one is that the spectrum construction, going from finitely presented algebras to a fine scheme, is an equivalence. So here on one hand you have algebraic objects, so the algebras. On the other hand you have objects that are more geometric, so affine scheme, which are the type of roots of some polynomials. And so you have an equivalence between the two, which is a key idea behind algebraic geometry. So another consequence is that any map between a fine scheme is actually defined by polynomials. So this is just a slight generalization of this, and so it means when you define a map in synthetic algebraic geometry, you never have to prove that it is a polynomial. It's just that any map you can define is a polynomial anyway. And so there's a third axiom, and I won't say much about it, but it says that a fine scheme enjoys a weakening of the axiom of choice that is called Zariski local choice, but I will not say more about it here. So now let's talk about smoothness. So first, I need the definition of a closed proposition. So I say that a proposition is closed if it is equivalent to the cancelling of R1 to Rn, a finite family of elements in R. So it's a proposition stating that a finite number of elements in R are closed. And so I won't get into the details here as well, but actually those are called closed because map from an affine scheme to the type of closed proposition correspond to the Zariski closed subscheme. And so that justifies the name. So there is a lemma that is not difficult, which says that given a closed proposition, the following are equivalent. So on one hand, you can have that the closed proposition actually asserts the cancelling of a finite number of nilpotent elements in the ring. So here the nilpotent is the new part, which was not here. And this is actually equivalent to asking that not P holds. So the equivalence between the two, it is because one can show that an element in the base ring is nilpotent if and only if it is not equal to 0. And so then those propositions are closed dense, are called closed dense. Okay. And so from here we can define smoothness for any type. So we say that a type is smooth if given any closed dense proposition P, the canonical map here sending a point in X to the constant map with value this point is surjective. And so if we unpack what this means a little bit, it means that for any point here, so for any map from P to X, we can merely find an element in the fiber of this map, which means that we can merely find a lift for this diagram. And so one perhaps more intuitive way to formulate it is to say that if we want to show that a smooth type is merely inhabited, we are allowed to cancel finitely many nilpotent elements in the base ring while trying to do this. Okay, but so now a very natural question to ask is what does this have to do with smoothness in the sense of absence of singularity that I mentioned earlier? And so that's what I want to explain. And so to explain this, I will only consider a fine scheme. So specialize this general notion of smoothness to a fine scheme. So first, let's give a very simple example. So you have an affine scheme which is called the line, which is simply the spectrum of Rx. And so it is smooth. So this corresponds with the geometric image of a line. And so how to prove this? So we assume a closed dense proposition. So it cancels finitely many nilpotent elements R1 to Rn. We assume a map from here to R, and we try to merely find a lift here. And so here the idea is to use duality. So actually, you have the diagram the other way, and you have that R is the spectrum of Rx. You can prove that this proposition is actually the spectrum of R quotiented by this finitely generated ideal. And well, the spectrum of R is obviously 1. And so then in order to find a lift, we just need to find a lift here, but this map here is surjective, so we can find such a lift. Okay, so now let's look at a non-example. So here the proof will be perhaps a bit more surprising. So let's consider this affine scheme. So the set of x and y in the base ring which product are 0. So this you can picture as the intersection of two lines in the plane. And so we expect it to be not smooth because at the point around 0 you have an intersection, so singularity. And in this is the case. And so to prove this, what we will do is that in the first step we will assume an epsilon in the base ring which has cube 0. And from this we will conclude that it has square 0. And then I will explain why this is a contradiction. So let us assume the type smooth. We look at this diagram here. So we send x to epsilon, y to epsilon. Here we have quotiented by epsilon square, so indeed the product of the image of x and y is 0. And so by the assumed smoothness of this spectrum, we can merely find a lift here. And so what does it mean? Well, it means that we have a map that sends x to something sent to epsilon modulo epsilon square. So we have an R in epsilon square such that x is sent to epsilon plus R. Similarly, y is sent to epsilon plus R prime. And for this map to be well defined, we need the product of the image to be 0. So this gives us this equation over here. And actually, using the fact that epsilon square is equal to 0, we see that this expression here is just epsilon square. And so we conclude that epsilon square is equal to 0. And so now a natural question is, well, why is this a contradiction? Well, actually, since you have that epsilon square, epsilon cube equals 0 implies epsilon square equals 0, you have that these two types are actually equal, because the other implication is obvious. And then you use duality to get that those two R algebras are equal. And this, you can see, this is a contradiction. So for example, as R module, this is R2 and this is R3. So one can show that they cannot be equal. Okay. So now let's go toward a bit more general consideration. So I want to define the tangent space to an affine scheme. So first I define D as this spectrum here. So it's the set of elements in the base ring which have a square 0. And so this is pointed by 0. And you should picture this as like a point 0 with some infinitesimal information around it. So kind of a fat point in some sense. And so from using this type, given any type x and point in x, you can define the tangent space of x at this point simply as map from D to x, which sends 0 to P. And so such a map, it has to send the infinitesimal information around 0 in D to some infinitesimal information around P in X. And this is actually a tangent vector, so by definition. So now we have a couple of easy constructions. So you have a tangent bundle, which is the map that evaluates at 0 any map from D to X. And the fiber over any point in X is easily seen to be the tangent space at this point. Okay, and you can also define differentials. So you assume given a map from X to Y and a point in X, and you want to have a differential between the appropriate tangent space. And actually, it's enough to just post-compose the map here with F, and you have to check that the equality are preserved. Okay. So first proposition where I will not explain the proof at all, but I will use to prove some other thing. So let us assume a map between affine scheme. Let us assume that the target is smooth. Then the following are equivalent. So on one hand, the fiber of the map are smooth, and on the other hand, the differential are surjective. So this corresponds to the idea of submersion in differential geometry. So a map between smooth objects with a surjective differential has smooth fibers. So okay, so we can prove this. I will not explain why. But using this, we can prove something about tangent spaces of smooth affine scheme. So I need to give a couple of definitions. So an R module is finite free if it is of the form Rk for some natural number k. Okay, and it is finitely co-presented if it is the kernel of a linear map between finite free module. So yeah, so it's the dual of being finitely presented, which means being the co-kernel of such a map. And so then the proposition is that let X be an affine scheme with a point, then the tangent space at this point is finite free. So it is of this form. And so that matched the intuition of smooth, meaning having no singularity. It means at least that the tangent space at each point are nice. So the general idea of the proof. So first, you use the fact that tangent spaces of affine scheme are finitely co-presented. So this I will not explain. Then you have to prove that tangent space of smooth affine schemes are themselves smooth types. And then you conclude by saying that smooth finitely co-presented modules are actually finite free. So let me do the second step first. So assume a smooth affine scheme, then the tangent space is smooth. So here we want to use the proposition that I mentioned. So what we need to show actually is that the fiber of this tangent bundle are smooth. And so to prove this, first we have that both types are affine scheme. So X, this is true by assumption. And for this one, you can see it in different ways, but one way is to use the fact that this is a sigma type of X and tangent space. And tangent space are finitely co-presented, so they are a set of roots of linear polynomials. So in particular, they are a set of roots of polynomial, and they are affine schemes. So you have that X to the power of D is smooth because D has choice. So this is something very general you can prove about merely having a lift, basically. So then we just need to check that the differential are surjective. And so actually, what does it mean? It means that for any such diagram where here the map send 1 to 0, and this one evaluate at 0, we need to merely find a lift. So here, a map from D to X, this is a tangent vector to X. And the lift here is a tangent vector in X to the power of D, which is sent to this X. And so this part here just say that the base point is the right one. Okay. So now you can use the pullback exponential and push-out product adjunction to know that you just need to merely find a lift in this diagram here, where here you have two copies of D that you include in T times D as the two axes. And so how to find such a lift? Where a key remark is that D times D has choice. So in order to merely find a lift, we just need to merely find a lift over any point here. So it means that for all pair here in the product D times D, we need to find a lift this diagram here, where this is the fiber of this map over epsilon delta. And so, so we know that epsilon square and delta square are 0. So we know that we can find a lift against, using delta equals 0 and epsilon equals 0. And you just have to prove that you can glue the lift together to get a lift with the OR, but that's fine. Okay. And so, so now we know that the tangent space are smooth. And so let me quickly explain how you prove that it implies they are finite free. So you consider a map with a smooth kernel, and you want to show that the map is equal to 0 or different of 0. So something I don't explain is that it's actually enough to prove that m equals 0 is not stable. So let's do this. Assume not m equals 0. Let's consider a basis of Rm. So if m is equal to 0, then xy belong to the kernel, because m is equal to 0. Since we have not m equals 0, this is actually a closed dense proposition, saying that all the coefficients in the matrix corresponding to m are 0. So you merely have a lift over here. And then you want to show that this lifts from a basis of Rm and conclude that m is equal to 0. And so to do this, if m is equal to 0, then the lifts are equal to the original one, and they form a basis by hypothesis. You have not m equals 0, but being a basis, it means that some determinant is different of 0. So in particular, it's not stable. And so from this, you conclude that the y are indeed a basis. And so that m is equal to 0. Okay, and very quickly, so let us assume, again, a linear map with a smooth kernel. We want to prove that the kernel is finite free. So the idea we do by induction on m, apply the previous lemma. If m is equal to 0, this is immediate, the kernel is the whole thing. And if m is different of 0, then we know that one of the coefficients of the matrix corresponding to m is different of 0. So it's actually invertible. And then we can use Gaussian elimination using this invertible element to go back to m-1. And so that concludes the proof that tangent space to smooth affine scheme are finite free. And that concludes my talk. Thank you.
Do we have any questions for Hugo? Okay.
So I know synthetic differential geometry. So is your definition of smoothness also motivated by synthetic differential geometry, or is there some connection?
So the precise connection is unclear to me.
Okay.
The main motivation for the definition of smoothness is actually the definition of étalness, where you ask not that there merely exists a lift, but there exists a unique lift. But it's unclear to me how it connects to synthetic differential geometry, especially because here it's very key that we use proposition and not infinitesimal extension of the points. So here there is a mismatch that I'm not sure how to make sense of.
Any other questions? Oh, I have a quick question. So is this proof, is this modeled on a proof that's in the literature, or is this, how far does this deviate? I'm curious from...
It's not modeled on a proof in the literature.
Okay, so this is a kind of new synthetic proof
yeah.
Really that's different.
Yeah, I think, yeah, and the key idea, which is to prove the tangent space of a smooth scheme smooth, it's not super clear.
Okay.
I mean, I don't know. I haven't encountered this in the literature, at least.
Okay.
Yeah.
Yeah, Jonas?
Following up to this question, is it clear how your concepts relate to classical concepts? Because there's this awkward issue of like how precisely the internal definitions correspond to external definitions, I think.
This is not clear at the moment.
Okay.
But yeah, that's a very good question indeed.
Okay, we have one more.
Yeah, I just have probably a question just about the definition of smoothness. And so here you rely on the double negation. And so in a sense, one could interpret this definition of smoothness in some tuples, even elementary. How are there like certain examples, let's say, where this kind of smoothness reduces to something that is maybe unexpected or something? If it's clear what I'm asking.
Not so much, because to me this definition of smoothness rely in a key way on having a base ring.
Mm-hmm.
So I mean, is your question, can you do this
Yes.
using any ring?
So what I meant to say was, so here, I mean, you characterize smoothness in terms of these closed, dense properties.
Mm-hmm.
So, but you know that this is indeed equivalent to using, the TUFs, let's call it a factorization, in these terms of this arise being 0. But you show that this is equivalent to the proposition that it satisfies double negation. And so if you can remove, let's say, the algebra structure and just look at the double negation, and in this way, then you can interpret this. If you have something like, I don't know, like Lavier topology or something.
So I don't have a particular example of this in mind.
Okay, thanks.
Okay, so let's thank you, Hugo, again. Thanks.
Thank you.